Today we will be doing a solved example on the topic vector spaces. So the question is, determine whether the set V of all pairs of real numbers x comma y with the operations x1 comma y1 plus x2 comma y2 is x1 plus x2 plus 1 comma y1 plus y2 plus 1, and the second operation k times xy gives kx comma ky is a vector space. So in this example we have been given these two operations and we have to prove that V is a vector space given these operations are to be carried out on all the vectors in this space having the form x comma y, and x and y are real numbers. So to prove this we have to prove 10 axioms. So in this type of questions we will first assume the vectors from this space V and then we will prove all the 10 axioms. So we will take that let u is equal to x1 comma y1, v is equal to x2 comma y2, and w is equal to x3 comma y3 are objects in V and k1 comma k2 are scalars. So we will be taking two scalars which will be used in our properties. So first axiom is, we will first find out u plus v is equal to x1 comma y1 plus x2 comma y2, x2 comma y2, which will be equal to, now using this operation which is defined in this set V, so we'll use this operation for addition. So it will become x1 plus x2 plus 1 comma y1 plus y2 plus 1. Now since x1 y1 x2 y2 are real numbers, because it is given that x and this pair are real numbers, therefore x1 plus x2 plus 1 is also real and y1 plus y2 plus 1 are real. Therefore u plus v also belongs to V. So and are objects of V. So now we have found out the value of u plus v because we were given this operations. U plus v, both the coordinates of this is real, so we can say that u plus v belongs to this set V. So we can say that V is closed. Now second axiom. So first axiom is true. Second axiom we will say u plus v is equal to, again the same thing will come here, x1 plus x2 plus 1 comma y1 plus y2 plus 1, which is equal to x2 plus x1 plus 1. Now I am writing this in the reverse condition. I'll say y2 plus y1 plus 1. This is equal to v plus u, because if we will do v plus u, then we will get this answer. So this is v plus u. So we can say that hence vector addition is commutative. So we have shown that u plus v is v plus u, hence this is commutative. So second axiom is also true, vector is commutative. Now third, we will find u plus v plus w. So u is x1 comma y1 and v plus w will be x2 plus x3 plus 1 comma y2 plus y3 plus 1. This is coming from this addition law. Now this will be x1 plus x2 plus x3 plus 2 comma y1 plus y2 plus y3 plus 2, using the same law. So I can write it as x1 plus x2 plus 1 plus x3 plus 1 comma y1 plus y2 plus 1 plus y3 plus 1. So again this is nothing but u plus v, and we are adding w here, so this becomes u plus v plus w. So again we can say that vector addition is associative. Therefore vector addition is associative. So hence third is also proved. Now fourth one. So when we'll do fourth one, we will have to assume an object a comma b in V such that a comma b plus u is equal to u. Now we have to find a zero vector in this vector space V. So let a comma b be a value such that addition of it will with u will give us u. So a comma b plus u is x1 comma y1 is x1 comma y1. Now a plus x1 plus 1, now adding this with the same property, comma b plus y1 plus 1 is x1 comma y1. Now equating both the coordinates, we get a plus 1 plus x1 equal to x1 and b plus y1 plus 1 equal to y1. So we will get a plus 1 equal to 0 and b plus 1 equal to 0. Therefore a equal to minus 1, b equal to minus 1. Therefore minus 1 comma minus 1 is the zero vector in V. So we have found out the zero vector in V. So now we have done the fourth one from here. Now we will do the fifth axiom. That is, now we have to find a unit vector, the negative vector of u. So let a comma b be an object in V. Similarly, like we have done in the above, now u plus a comma b is equal to 0. Zero vector is minus 1 comma minus 1. So we are going to find out the negative of u here. Now this is zero vector, so it is like u plus minus u equal to 0. This is the idea. So here zero vector is nothing but minus 1 comma minus 1, and the negative we will be going to find out. So x1 comma y1 plus a comma b is minus 1 comma minus 1. Now again the same addition rule, x1 plus a plus 1 comma y1 plus b plus 1 equal to minus 1 comma minus 1. Equating both the coordinates, we get x1 plus a plus 1 equal to minus 1 and y1 plus b plus 1 is equal to minus 1. So therefore the negative of u will be minus x1 minus 2 comma minus y1 minus 2. So while solving we will get the values of a and b as this and this, and so this is the negative of u in V, set V. Now we will do the sixth axiom. So this is k1 times u is equal to k1 into x1 comma y1 is equal to, now we will use the second property of multiplication, which is nothing but kx comma ky. So we will use it here, k1 x1 comma k1 y1. So this is the property used here. Now we will say that both k1 x1 and k1 y1 are real. Hence k1 u also is an object of V. Hence V is closed under scalar multiplication. Scalar multiplication. So the sixth one is also proved. Now seventh one is k1 into u plus v is equal to k1 into x1 plus x2 plus 1 comma y1 plus y2 plus 1, which will be equal to k1 times x1 plus k1 times x2 plus k1 comma k1 times y1 plus k1 y2 plus k1. So this is not equal to k1u plus k1v. Now actually this axiom must be true, that is k1u plus v must be equal to k1u plus k1v, but here in this case this is not true. We can see that k1u plus k1v will not give us this result. So we can say that v is not distributive under scalar multiplication, because the vectors are not distributing it under the scalar multiple k1. So we will say this. Scalar multiplication. So we have completed 7 axioms. Since this is not true, we will not going to be solved further 8, 9, 10. So we can directly say that hence V is not a vector space. So we can directly write that V is not a vector space. If we can see that if we will do k1u plus k1v, we will be getting the answer as k1x1 plus k1x2 plus 1, but here we are getting k1. So this is the difference. So this is not equal. So we can say that it is not a vector space. This is our final answer. So we have to show all the axioms until we get an axiom which does not satisfy the condition. So this was the solution. Thank you.